Keeping up with all the advancements in machine learning, especially with these big vision language models, it's a lot, isn't it?
It really is.
I mean, you just get used to one thing, and then something new and amazing pops up. But today, let's look at something really interesting that's trying to make this visual instruction tuning, the process, well, a little easier and more accessible because it's pretty resource intensive.
Absolutely. We've all seen what these large LVLMs can do. I mean, they're doing some pretty remarkable stuff, but the amount of data they need, it's huge. We're talking massive data sets of image instruction pairs.
Yeah.
And someone has to create those instructions, whether it's a person or we're using something like the GPT API. That all costs money and time.
Yeah, it's a barrier to entry for sure.
Yeah, it can really limit who gets to work with this kind of technology. Researchers, developers. It's a problem.
For sure. So today we're diving into a really clever approach that, well, it kind of flips the whole data thing on its head. Instead of starting with tons of data, all these images with instructions already attached. This paper, it's called Filter Images First, Generate Instructions Later, Pre-Instruction Data Selection for Visual Instruction Tuning. They have this idea that what if we first pick out the best unlabeled images and then make the instructions just for those?
Interesting.
It's all about being a bit smarter about how you build your training data.
Right.
Use your resources wisely, right?
Makes sense. I like it.
So
this,
go ahead.
this pre-instruction data selection thing, they call it pre-sell. This could really change things up,
Yeah.
Not only could it save us a ton of computing power when making all those instructions, but it might even speed up the whole fine-tuning process for these big models too.
Yeah, I see that. So they're essentially asking, you have this giant pool of images, all kinds of images for different tasks. How do you pick out the best ones for your model to learn from before you go through all the trouble of, explaining what's in them? Okay, so let's dig into pre-sell, how it works. The paper talks about how it's a totally different way to look at the data we use for this visual instruction tuning stuff. Instead of picking through existing data sets that already have all those instructions, they say, let's just start with the raw images first.
From scratch.
Yeah, and by doing that, they're aiming to save resources in a couple of ways. Less computing power needed to make those instructions and quicker fine-tuning later on.
And, this whole idea of making this tech more accessible, that's a big deal. The authors make a really good point about how expensive it is to build these huge, high-quality data sets with images and instructions. If you're doing it manually with people, well, that's costly. And if you're constantly using APIs like GPT, that adds up too.
Yeah, it's a real obstacle.
Absolutely. So pre-sell is really trying to tackle that problem head on.
Right. So let's break down exactly how pre-sell works. The paper lays it out like this. Imagine you have this huge collection of images, right? And they come from all these different vision tasks.
Okay, so we're talking about like answering questions about what's in an image or finding text in a picture or pinpointing where different objects are, things like that.
Exactly. Now, the thing that takes up the most time and resources, it's turning these plain images into, usable data for training.
You mean by making the instructions for them?
Yeah, telling the model what it should be learning from each image. And that can be a ton of work, whether you're using humans to do it or relying on AI.
Okay, but they're not saying we should just randomly pick images to make instructions for, right?
Right. That's the whole idea behind pre-instruction data selection. It's about choosing a specific set of these images before we do anything else. And the goal, to train an LVLM using this smaller, more carefully selected set and get results that are just as good as if we'd trained it on the whole huge data set.
Wow, so trying to be as efficient as possible.
Exactly. So pre-sell, how they do it, it's a two-step process. First, you figure out which of those different vision tasks are the most important. They call that task importance estimation. Then you go into each of those tasks and you pick out the most representative images.
Gotcha. So let's talk about that first step, task importance estimation. What do they find?
Well, they noticed that a lot of these data sets for visual instruction tuning, the data is kind of like unevenly spread across different tasks. Just because you have tons of images for, say, making captions, that doesn't mean captioning is the most important thing for your model to learn.
Right. Some skills might be more valuable than others.
Exactly. And some of the methods they've used to try and balance things out, they're kind of like rule of thumb approaches, not really based on solid theory. So their approach, it's based on actually testing things out.
Empirically driven, I like it.
So what they do is they take a small sample of images, like 5%, from each of the tasks in their data pool, and then They go ahead and create instructions just for this small set.
Okay, so this is just a tiny fraction of the total data.
Exactly, a much smaller investment to start with. Now, this smaller set, it's crucial because they use it to see how relevant the instructions are for each task. And for this, they have this thing called an instruction relevance score.
IRS.
Catchy, right. The way they calculate it is pretty neat.
I'm curious, how do they do it?
They measure how well their model can answer a question about an image when it's given the question compared to when it only has the image itself.
So like, are the instructions actually helping the model understand the image better?
Exactly. So they're doing these two calculations. One where they look at what the model predicts when it has both the image and the question, and the other where it only has the picture. The IRS, it's just the ratio of those two.
So a high IRS means the question wasn't really that helpful.
Right. It means the model could figure out the answer pretty well even without the instructions.
Which suggests maybe that task isn't super crucial for the LVLM to learn.
Exactly. And on the flip side, if the IRS is low, that means the instructions were really important for guiding the model towards the right answer. So that task, probably something the model should focus on.
That makes sense. So how do they use these scores to figure out the task importance overall?
Well, first, they get an average score for each task by looking at all the images in that small sample set. That gives them an overall idea of how important that particular task is. Then they use a bit of math, some calculations with an inverse exponential function and a temperature parameter, and they turn those scores into something called task-specific sampling budgets.
Okay.
These budgets basically tell them what percentage of the final data set they should take from each task.
So stage 1 is all about figuring out the what. What are the important tasks?
Right. Then we move on to stage 2, which is all about picking the right images within each of those tasks.
And this is where it gets really interesting, I think, because even after you've figured out which tasks are important, you could still have thousands, millions of images for each one.
Exactly. So they need a way to pick out the best ones without going through the trouble of creating instructions for all of them. And here's where they use this really cool tool, a lightweight vision encoder called Dyno V2.
Dyno V2, I've heard of that.
It's a model that's already been trained to understand images. It can extract these really meaningful visual features from the images without needing any extra labels or anything. So they use Dyno V2 to analyze all the unlabeled images in each task.
And then what?
Well, here's the clever part. They do clustering on those features separately for each task.
Clustering. What's that?
It's like grouping similar things together.
Okay.
So they use this algorithm called k-means, and they group together images that look similar based on what Dyno V2 found, and the number of groups they make for each task. It depends on how many images there are for that task to begin with.
So more images mean more groups.
Exactly. And remember those task importance weights we talked about earlier?
Budgets?
Yeah, those come into play here. So for each group within a task, how many images they pick depends on two things. How big is the group? And how important is the overall task?
So more important tasks and visually diverse clusters will have more images selected.
Exactly. And they don't just pick randomly from those groups either. They have another trick up their sleeve.
Oh, what is it?
It's called the neighbor centrality score. So for each image in a group, they find its closest neighbors, like images that look really similar based on what Dyno V2 found, and they calculate how similar that image is to its neighbors.
So images that are kind of in the center of their group that are very representative of that group get a higher score.
Right. So they try to pick those more central images because they're like the best examples of what that group is all about.
Makes sense.
So once they've done all this, gone through each task, done the clustering, and picked the most representative images, that's when they finally make the instructions just for that specific set.
That's where the real savings come in.
Exactly. Now, the big question is, does this whole thing actually work? Well, they did a bunch of experiments to test it out, and the results, pretty impressive. They used two huge data sets, a Lavier 1.5 and Vision Flan. And here's the thing. They pretended that only the images were available, like they didn't have any of the instructions beforehand.
Ah, so just like in a real world scenario.
Right. And guess what? By making instructions for just 15% of the images, they got performance that was almost as good as if they'd used all the images.
Wow.
Yeah, it's a massive savings.
Huge.
They also compared pre-cell to a whole bunch of other methods for picking images, some simple ones and some really fancy ones, and pre-cell beat them all, especially on this LLVA 1.5 dataset.
And how about on that other one, Vision Flan?
On Vision Flan, which is even more diverse, it has like almost 200 different tasks. Precell did amazingly well. It even beat a model trained on the entire Vision Flan dataset.
Wow, that's remarkable. So it's not just good for a few specific tasks, it can handle a whole lot of them.
Exactly. They also looked at what happens when you change how many images you pick, and they found that most methods get better as you use more images. Makes sense. But just randomly picking images, it actually starts to get worse after a certain point.
Interesting. So there is a point where just throwing more data at the problem doesn't help.
Yeah. But Precell, it kept getting better and better.
Okay, so they're saving time and money on instructions. But what about the computational resources for the selection process itself? How does Precell compare to other methods there?
Well, they did a comparison with some other really advanced methods like coincide and self-filter, and Precell used less GPU power, which is good.
But the real savings come from those instructions.
Yeah, because you're only making them for a small part of the data. Other methods have to make them for everything, and that's expensive.
It all adds up.
They also really dug into each piece of Precell to see what was actually making the biggest difference, and they found that the task importance estimation part, that's crucial.
Yeah, makes sense. Got to know what to focus on.
Right. And both the clustering part and that neighbor centrality score for picking good examples, those are important too. They even tested different values for that K parameter in the neighbor centrality calculation, and it turned out to be pretty stable.
So they really did their homework, made sure it's robust. That's good to see.
They even tested how well Precell would work with different types of LVLMs, not just the one they used to pick the images. And it still worked really well, so it's not just a one-trick pony, it's pretty adaptable.
That's impressive. It's interesting to think about how this research fits into the bigger picture of making these AI models more, practical. For a long time, we've relied on these gigantic data sets where every single image is labeled by hand.
ImageNet, yeah.
ImageNet. And those labels, they're expensive. But as these vision language tasks get more complex, it's becoming almost impossible to keep up with labeling everything by hand.
So then came these models like GPT that can generate data.
Right, but those have their own costs, as we've been talking about.
True. So Precell comes along, and it's like the smarter way to use all those unlabeled images that are just sitting out there. It's building on ideas from things like active learning, where the model kind of tells you what data it needs to learn better.
It's all about making those labeling resources count.
Exactly. So to sum it all up, Precell tackles this big problem of how much it costs to make instructions for all those images. And by doing that, it makes it much easier for, anyone really, to create custom data sets that are perfect for their specific needs.
Yeah, without breaking the bank.
The task importance part, that's super smart because it helps you figure out what's really worth focusing on, and the clustering and the neighbor centrality stuff. That ensures you get a really good, diverse set of images without picking any weird outliers. And in the end, they're getting great results with a much smaller, much cheaper data set. That's pretty huge.
Absolutely. So what do you think about the real-world impact of all this? What could this mean, practically speaking?
I think it really changed the game. It's like opening the door for more people to work with these powerful LVLMs.
Democratization of AI. Love it.
Right. Not just big companies with huge budgets. And I think it could speed up how quickly we develop new LVLMs, because the whole process from getting the data to training the models becomes a lot more efficient.
Faster iteration cycles. That's exciting.
And imagine creating these models for very specific uses, like in robotics or self-driving cars or even medical imaging. There's so much potential.
Absolutely. So I think time for a novel notion segment, right? Where we talk about some potential future research directions based on this paper. What are you thinking?
Yeah, I've got a couple of ideas brewing.
I'm all ears.
So that task importance estimation part, right. Right now, they do that at the very beginning with that small set of images. But what if, after they've done that initial selection and made instructions for that smaller set, they actually train a small LVLM on it?
So use that initial data to get a slightly smarter model.
Exactly. And then could they use that model to go back and reevaluate the rest of the unlabeled data? Maybe some tasks that seemed less important at first might turn out to be crucial later on.
Like an active learning loop, but at the task level.
Yeah, that's a good way to put it.
That's really interesting.
Yeah.
It could definitely uncover some more subtle dependencies between the different tasks that you might miss with just that one initial assessment.
Exactly. And my other idea, it's about that Dyno v2 model they used.
Okay.
Remember how they used it to get those visual features and do the clustering? Well, models like Dyno v2, sometimes they're not totally sure about those features, especially for images they haven't seen a lot of before. What if they use that uncertainty as another way to pick images?
So you're thinking, instead of just focusing on images that are typical of their group, you'd also want to pick images where Dyno V2 is less confident.
Yeah, like those images might be harder for the model to understand, so they might be even more valuable for training.
That makes sense.
Yeah.
It's like you're deliberately choosing the images that will challenge the model the most, and that could make it more robust in the long run.
Right. Instead of just sticking to the easy stuff, it's like, let's make it work for it.
Exactly. And it ties in nicely with some ideas from active learning, too.
Yeah, it's all connected.
Of course, these are just ideas, things to think about and explore, but it's really cool to see how all these different research areas can come together.
It's fascinating.
It is.
So, to wrap things up, this pre-instruction data selection stuff, it's a really promising way to make these LVLMs more efficient and, less costly to train. And the fact that they're getting such good results with way less data, that's a game changer.
It really is.
We'll definitely put a link to the paper in the show notes for anyone who wants to dig into the nitty-gritty details.
Absolutely.
And it really makes you think, could we use this same idea, this pre-selection thing, in other areas of AI where we're working with multiple types of data? There's so much to explore.
So much.
Well, this has been a great deep dive. Thanks for joining us.